To everybody. Here today we'll have a lecture series on the derivation of the Lorentz transformations. The Lorentz transformation equations play a vital role in physics, especially in special relativity, as submitted in the seminal papers of Einstein in 1905. They are named after Henrik Anton Lorentz, a great scientist who predicted the results by another theory, the theory of ether, contraction and so on. But the results amazingly quite if we remove the approximations, quite touched Einstein's transformations for inertial frames, and we will derive it today using simple principles. The Galilean transformation, as you know, is given by x dash equals to x minus vt, is it not? Let this be x-axis and let this be time axis. Then if something moves, particle moves along this direction, then the Galilean transformation gives you the coordinate of the particle in the particle frame, the coordinate in the particle frame x dash. Okay, and the time remains the same, time equals to time dash. This is one of the transformations that may be possible, but in real world, in order that the Maxwell's equations of motions hold true, Henry Poincaré suggested and proved that a Lorentz transformation would be the suitable one that would transform the Maxwell equations and make them invariant in different frames. He first of all postulated that the laws of physics are the same in all reference frames, and that is you cannot distinguish reference frame from another reference frame moving at the same velocity as the moving at a constant velocity with respect to the first one. All of these talks are about inertial frames, that is frames in which Newton's equations hold true. Okay, now we will directly go into the Einstein's picture and how he derived the Lorentz transformations. Though they look very cranky, yet the equations, when adequately arranged, look beautiful. There is beauty in the equation, the beauty that Dirac searched for. So what Einstein did was this: he took a set of axes O, then here x, and here t. Okay, then he considered a moving vehicle starting from rest at origin and traversing a path at a velocity v. Then equation of motion of the trajectory will be x equals to v times t, where v is the slope of the graph or the velocity. Here he then considered another frame of reference. Now why he considered this, I'll tell you later. X equals to vt plus 1. That means it is one shifted from that position. one shifted always it is, and let there be another line, and it will be x equals to vt plus 2. Why he took all this? What was the necessity? The necessity was what we call now simultaneity. And what is simultaneity? Consider a train, and we take the midway in the train, and I am the detector, and here from the front and the rear ends light flashes are there. If I am just in the middle of the frame, then what will happen, that the light flash from the rear end and the light flash from the front end will come to my detector in the same time. And why they will come to my detector at the same time? Because the speed of light is constant in all reference frames, and that was one of the postulates of special relativity. The first postulate, the speed of light is constant in all inertial frame. Remember, inertial frames, these are not accelerated frames or frames in which gravity works. We are talking simply of special relativity. And second, the law given by Poincare that all physical phenomena cannot be distinguished in inertial frames. Physical phenomena are consistent. These two also in inertial frame. These two are the suggestions made by Einstein, postulated by Einstein, in order to come to the results of the general theory of relativity. Now, if I see this from outside, I'll see that if I am here midway now if a light flash is thrown from here, so due to my translational velocity, I'll go to a certain distant point. So the light flash will take much longer time to arrive at me, whereas the light flash that was thrown from this direction, this will find the midway at a much earlier time. Hence, it will reach the midway faster than the rear end. So this thing, we see that things that are simultaneous in this frame are not simultaneous in this frame. So this is what we call the breakdown of simultaneity. Okay, now we'll wrap this all and consider simultaneity in greater detail. Okay, now what will be my system of coordinates, or how will I synchronize my clock, or know at what region am I? So for this we have other axes. Not if we consider the rest frame of reference, then x and t gives us all the information. At least x and t gives us the trajectory of the particle. But if in the inertial frames, what happens? What happens inside the train or inside the car, in which they let this be called I, J and K. The car in which I, J and K are seated will have different equations of motion. So what will be simultaneity for them? We'll discover, we'll unravel. Okay, now simultaneity, let us consider ad hoc first, that when they were everything at rest, that means I was at rest, J was at rest, K was at rest, then I was at rest. I threw a light beam towards J, and K threw also a light beam towards J, and if both the light beams meet at the same time, then they are said to be simultaneous in that frame, because the speed of light is constant. That was the idea of Einstein. So he considered light being thrown from I to J, but light being thrown from I to J will be like this, will have a 45-degree slope, because here we consider c equals to 1, or speed of light is equals to 1. What is the distance traveled by light in 1 second? 1 light second. Yes. What is the distance traveled in 1 year? It is 1 light year. 1 week in 1 light week, is it not? So 1 by 1 gives you 1, then this gives the speed of light equals to 1. So we propose this in order to avoid cluttering of the equations. Okay, now another light which is thrown from K to J. Now this light which will be thrown from K to J, since all of them are going in this direction, so the light thrown from K to J will can be thrown at a later time, in order that they simultaneously meet at the point say P. So I am taking a later time, and but the slope will remain the same, only it will have a minus or negative sign. The slope will remain the same because the speed of light is constant. So here slope is +1, here slope is -1. Okay, now we will do certain equations and solve the equations, and we'll go away. Let us first solve what will be the coordinates of P. We know that P is governed by the equations first x equals to t, or t equals x. T equals x. Here t equals x, and here x equals to vt plus 1. X equals to vt plus 1. Just substitute the value of x, then t equals vt plus 1, and then t times 1 minus v equals 1, or t equals 1 by 1 minus v. Am I right? Okay. Now just go on to solve the other equations. Now we can also find the coordinates of Q. Okay, we find only one coordinate of P. Now we will find the second coordinate now. Now T is given by this. Now x is equals to T, then x is given by also 1 by 1 minus v. Okay, now for Q, what are the equations of Q? The first equation is x equals to c. The slope of the graph is minus c. Minus c means -1. Then x equals to minus t. T equals to minus x plus some constant. We'll name the constant n. Okay, to distinguish it from m, which is given by the slope. So t equals to minus x plus n. And another equation is for Q, x equals to vt plus 2. X equals to vt plus 2. Okay, we have to solve these two equations. But the first equation is minus x plus n, but the first equation holds for the the trajectory of the light pulse here from P to Q. So it holds at P. So as it holds at P, we'll take the value of t at P. 1 by 1 minus v is equals to c t, and the value of x is 1 by 1 minus v, and minus 1 by 1 minus v plus n. This gives n equals to 2 by 1 minus v. Okay, we have the value of n. Okay, now we have the value of n. We will substitute something. X equals vt plus 2. If we can substitute something called x, then from the second equation we can extract the value of t. So how can we get x? Now x now we know that t equals to minus x plus n is the equation of motion of this. So it follows p. So we just write the equation of p to get n. Okay. The value of t at the time is 1 by 1 minus v. Okay, x minus x plus n plus n. Then okay, let us place this value of n in the first equation. This gives t equals to minus x plus 2 by 1 minus v. Okay, now we have x equals to x goes here to this side, so 2 by 1 minus v minus t, is it not? Yes. Okay, now we'll substitute something, this thing in this thing, then 2 by 1 minus v minus t equals to vt plus 2. Okay, will this give us a result? Okay, let's see. Then v plus 1 times time becomes 2 by 1 minus v minus 2. Then this gives us 1 minus v, 2 minus 2, 0, plus 2v. Okay, then time equals 2v by 1 minus v by 1 plus v, 1 minus v square. Okay, sorry, 1 minus v square. Okay, so this is the time. This is the time at which this is the time at which the signal will reach at point P. The time at which the signal will reach at point P. Okay, and distance, the position of point P is given by 1 by 1 minus v, and the time, and so this is the position of P, this is the time of P. Now if we want something, a triangulation relation, then let us see what are the let us see here what is the time that we have calculated? The time is the here the time that we have calculated is the time with the time of the time after the at which the signal is sent from Q. I think yes, the time at which the signal is sent from Q. And we have the value of X also. Yes, this is the time at which the signal is sent from Q but does not reach P. Okay, by the time Q reaches a little more distance. Okay, this is the time at which the signal is sent from Q. Now what is the corresponding X or the position of Q? The position of Q is given by X equals to Vt plus 2. Vt plus 2. Handling my camera is becoming more and more cumbersome. I required a stand, but who will give me money? Plus 2. This 2 becomes 2 minus 2v square. Okay, 2v square cancels 2v square, then it is 2 by 1 minus v square, isn't it? Okay, the first thing was 2v by 1 minus v square, and second thing is x equals to 2 by 1 minus v square. These two things are very important things. If my ink would be indelible, I would not have passed an examination. 1 minus v square v x equals to x equals to 2 by 1 minus v square. Okay, 2 by 1 minus v square. Okay, so we find a value of t, we find a value of x. So what is the value of t? This is the value of t. See, we just take another axis and any point, let this is the value of x and this is the value of t. Okay, here x. So if we do t by x, we will find tan theta. Okay, so we compute t by x and it comes out to be 2v by 1 minus v square by x. X is 2 by 1 minus v square. Everything cancel out mostly, and what remains is v, and t by x equals to v, then t equals to vx. See, we took the distance between them to be 1 1. Whatever you take the distance between them, you can take it a and a. The a will cancel out and will last get this equation, t equals vx. Though hence t equals vx is true for any such arranged frames. So if we put another frame inside this, just in the middle, and call that I, j, k, let that be L. Okay, then these two will follow the same graph, same tan theta. That means the angle that will connect here to here and to here will also connect here to here to Q. Okay, let us be more immaculate. Yes, this will be the condition, and whatever you take infinite amount of infinite number of such reference frames, but you will always get one straight line which will have a same slope given by t equals to vx, though v will be the slope of the graph. So this almost completes the argument, but we have to continue the argument a little bit more. I think I will take another lecture to show the rest of the thing. But here t equals to vx, so t minus vx equals to 0. We can write this as t dash equals to 0, just as we can write for x equals to vt, x minus vt equals to 0 gives x dash equals to 0. Why x dash? Just for example, there is someone, my friend, in a rest frame, and he is seeing me running at a constant velocity. Then he will have his own coordinates and he will see me running, but I will never see me running. I will see that my nose, which is in a particular position, remains at that position. That means for me x dash equals 0. So this thing motivated this thing, t dash equals to 0. Yes, so we have two equations here. We'll do this as x minus vt equals to 0 and t minus vx equals to 0. Now we can do one thing. We can call this here x minus vt, x dash equals to 0, t dash equals to 0. But if that would be the same, x dash equals to 0, t dash equals to 0, this would never give us the Lorentz transformations. That means if we take this to be t dash and this to be x dash, that will not yield the Lorentz transformation. Here see, this gives only Galilean variance, Galilean transformation, isn't it? Although this thing is quite intact, this thing is quite incomprehensible now, but we can add something of a linear term. So let us call it fv, a function of v, velocity, the frames, into x minus vt gives you x dash. We can say this. See, if this becomes 0, this becomes 0. So fv in the linear term, that becomes 0, and gv into t minus vx is equals to t dash. Okay, then fv and gv, t minus vx is equals to t dash. So what we observe is the same thing. If we see from the other frame, that is the frame of I, j and k, then we'll see the rest frame, which is now will be moving in the left direction, and the equation motion will remain somewhat like this: x plus x dash plus vt dash equals x. Just a reverse transformation. But see, the linear term remains consistent because this relates only the velocity of the particle. So velocity of the particle. Now take GV. You can, in similar terms, you can write T dash plus V X dash is equals to, here minus sign is changed by plus sign. You can follow it, is equals to T. So we are seeing that here is something which depends upon the velocity, but not on the in the direction of the velocity. It depends on the magnitude of the velocity rather. So Einstein concluded that let us use v square instead of v. So he give v square. Okay. They are functions of v squares. Okay. So now he knew one thing, that if x equals to t, then x dash equals to t dash. That is for a this is the equations of a light ray. So he used one of the equations, x dash equals to t dash. Just if we use this thing, x dash equals to t dash, we'll just get fv square equals to gv square. You just substitute these equations here or here, you will get fv square equals to gv square. So there is a constant, let us term it fv square, and let gv square be obsolete. Okay. So fv square is the term. So here we write everything f. Okay, f fv square, everything is fv square now. Okay, now fv square x dash plus vt dash equals to x, fv square t dash plus vx dash equals to t. So fv square is the term which we want to calculate. Okay, now how we will calculate this? We require some help. Okay, let us try to calculate fv square into x dash. Here x dash, we know x dash equals to fv square times x minus vt. Okay, plus vt dash, v into time dash, v into t dash. T dash is given by fv square t minus vx. Okay, so what does they give? fv square equals to x dash, and then fv square t minus vx equals to give you t dash. Okay, now this fv square x dash plus vt dash gives us x. Okay, okay, this gives us x. Then see, we will not write fv square again, we will write f instead of it. And f square x minus vt gives plus v t minus vx into f square is equals to x. Okay, then f square into x minus vt plus vt minus v square. Oh, I have certain problems regarding configuration of the equipments which I have, although all of them are impoverished. Okay, minus v square x is equals to x, minus vt cancels plus vt. Okay, then x times 1 minus v square equals, sorry, times f square gives x. Then f equals xx 1 here, 1 by 1 minus v2 square root. We have to take the positive root due to a certain condition which I will show another day. Have to take the positive root. So this is the thing that comes in the Lorentz transformation. So we'll write down the Lorentz transformation. Lorentz transformation in C equals to 1. And what are they? Lorentz transformation will be, first of all, we know that fv square into x minus vt is equals to x dash. Then x dash equals to 1 by root over 1 minus v square times x minus vt. This is the first transformation, and y dash is equals to y. This thing is something which you know, there will be no transformation of coordinates in the direction other than the boost direction. There will be no contraction, no time, no contraction along that direction. This is something which is predictive. Although there remains certain forms of uncertainty, okay, but z dash equals to z, and here the motion is along the x direction, and the thing is fv square into t minus vx equals to t dash, and t dash equals to 1 minus root over 1 minus v square t minus vx. These are the Lorentz transformation when c equals to 1. But when c not equals to 1, c equals to c, then what happens? We can show that just by budging the coordinates, in the various physical quantities involved. See, 1 minus v square, how can you subtract v square, square of a number, square of a velocity from 1? You can subtract only if it has the dimensions of a number. Dimensions of a number is 0. No mass, no length, no time. Then you can put c square here. So this becomes a number. The number minus number, you can show that. In the previous transformation, what we showed, that v square was in fact a number. Now my x minus vt, x minus velocity into time is distance, so this is consistent. So this will be the first equation, the second and the third, okay, and the fourth equation, 1 by root 1. Here again we have to include c square, then t minus vx, velocity into distance, and here is time. So what you can do, time minus velocity into distance, so velocity into distance, but we know that distance by time equals velocity. So if in order to make it time, we have to make it x by t, is it not? X by t, but it is not coming to that point. It is not coming to x by t. So what can you do? X by t, this is t, then x by velocity. The velocity would be down, but the velocity is up. So in order to cancel such effects, we cancel the effects by giving a c square downstairs. Is c square, then velocity will cut by velocity, then x by velocity will give you a time. There are other forms which will give you the same result, but these are easy to reckon. And I think that will be the end of the lecture today, although it seemed to be very long, but it is interesting, and it is something that has been taken from the original piece, the magnum opus. Thank you.